So today what we're going to talk about is something called slope fields. And slope fields are just a way that we can use, it's a method we can use to graph what the solution to a differential equation looks like. So this is a fairly simple differential equation we've got here, right? dy dx equals cosine of x. What does y equal?
Sine x.
Sine x plus some constant, right? Because we weren't given an initial condition here. It's sine x plus some constant. It could be plus 1, could be plus 1,000, could be minus pi, could be anything, basically, right? We got sine x plus some constant. So we know what the solution to this differential equation looks like. It looks like a sine curve. So what we're going to do is we're going to use this idea of the slope field that I haven't really talked about yet, but I'm going to explain, to sketch the graph of sine x as if we didn't know that that was the solution, because we're going to deal with some differential equations that we just aren't going to be able to solve, right? We won't be able to integrate the function that we're given, or you might be given a differential equation that involves multiple variables, x and y, and that's going to make it even more difficult to deal with. So that's going to be our goal. And so before we start doing this, before we really start using these slope fields, we need to think about what a derivative, what dy dx really means, right? What is a derivative? What's a derivative?
It's the slope.
It's a slope, right? A slope of what?
A rate of change.
Yeah, that's what a slope is, right? It's a rate of change, but like the derivative of a function represents what slope, like what kind of slope are we talking about?
Slope of a tangent line.
It's the slope of the line tangent to that function, right? And you remember back when we did linearization a long time ago, this idea of linearization was on a very, very small interval, the tangent line is a very accurate representation of the actual function. And so that's what we're going to do. We're going to try to use the slopes of the tangent lines, so the cosine x's for different x values through here, on a small scale to have a general idea of what the solution to that differential equation looks like, because the differential equation represents the slopes of the tangent lines. Does that make sense, the connection there between the differential equation and linearization and everything we're doing? Sort of. I mean, you probably don't have any clue how we're going to do it yet, but does all that relationship like between the things make sense?
Yes.
Okay. So now we're going to construct our slope field, which means what we're going to do is we're going to look at our differential equation and say, first off, our differential equation, dy dx equals cosine x, the derivative part of it, the cosine x, only has an x in it. True? There's no y's over here on the right-hand side. There's just a cosine x, right? There's just an x. There's no y's, which means that we don't need to worry about y values. The only thing we need to worry about plugging into this is x values. So we're going to say, what does dy dx equal if x equals 0? What does dy dx equal? Put in your 0.
1.
Right, should be 1, right? dy dx equals 1 if x equals 0, right? What does a line with a slope of 1 look like? Because remember, dy dx is just the slope. It should be like that, right? That's a slope of 1. True? Yeah. So anywhere where x is 0, so basically all along up and down the y-axis, I'm just going to draw a bunch of little lines that have a slope of 1. And if yours are just slightly off, it's not perfectly exactly 1, that's fine. We just want it to be pretty close. Okay. Good or no?
Good.
Okay, and like I said, the y values don't matter, right? Anywhere where x is 0, the slope should be 1. Now, what about What about if x is pi over 2? What would dy dx equal?
0.
Exactly. Right? If x is pi over 2, dy dx is 0, which means the slope should look like, there's our slope of 1, right? The slopes now should look like this, right? It should be horizontal. True? So
Yes.
we'll call this first thing here pi over 2, and we'll just draw a bunch of little slopes of 0. Good? What about if x is pi? What's dy dx going to be?
-1.
-1, which should look about like that. So over here at pi, I'm going to draw, oh, that wasn't very good. I'm going to draw a bunch of little slopes that are -1. And what about at 3 pi over 2?
0.
Should be back to 0, nice and flat and horizontal there. And when we get to 2 pi, what should we have?
One.
Back to 1. Right? Should look out like that. And I'm not going to write them all out in this, like all of this notation for the negative values, but if I was at negative pi over 2, it's going to be 0. And if I was at negative pi, it should be -1. And if I was here at negative 3 pi over 2, it should be 0. And here at negative 2 pi, it should be back at 1. And all we have to do to sketch the solution to the differential equation is pick some point that we're interested in. We might have said like, oh, we had an initial condition that we wanted to be at the origin, let's say. Well, at the origin, we'd start and we'd say it's got a slope of 1. It should be going up, and then it should flatten out so that by the time it gets to pi over 2, it has a slope of 0, which would be about like that. And then by the time it gets to pi, it should have gone back down to about a slope of -1. And by the time it got to down here at 3 pi over 2, it should have flattened out to 0 and then back up to 1 again. And it should do the same thing going this way and just sort of follow the trajectories of those slopes to sketch a curve that goes through them that has those as its slopes. And what do we end up with? It sure looks like a sine curve, doesn't it? Sine curve starts at the origin, right? It has the, it's between a minimum and a maximum, right? Where it starts here when x is 0, and it goes up, and it comes back down, and it goes back up, and it just oscillates back and forth, and we have a sine curve. And we could have picked any point up here. Suppose we chose this point right here. Well, we'd start at 0, slope down, become 0, slope up, and so on, down, 0, up, 0, down. And they're all just sine curves. Some of them are higher than others, some of them are lower than others, depending on the value of our constant, if we had an initial condition. But they should all come out to look just like y equals sine x plus or minus some number. Does that make sense?
Yes.
Cool. So that's the idea of the slope field. We use it to sketch the solution to our differential equation. Now this one, we knew what the solution to dy dx equals cosine x was, so we didn't really need a slope field, but it's a nice easy one where it's familiar functions and it should be easy to see. What we're going to do now is try to deal with one that we might not be able to integrate. So we probably can't integrate the square root of x squared minus x plus 1. Right? It's not that it's impossible to integrate that. It can be integrated. It's just we in Calc 1 don't have the tools to do it yet. But what we can do is we can plug in some x values to that, sketch some little pieces of the slopes, and construct a slope field that would show us about what the solution to that function or to this differential equation would look like through any point we choose. Okay? And so that's what we're going to try and do. Sound good? Anybody have any questions? Do we conceptually understand what it is we're doing?
Yeah, we're
Yeah.
drawing lines.
We're drawing lines, but that's not conceptually what we're doing. That's physically what we're doing. We're drawing lines. The conceptual part of this is we are using the derivative as a tangent line to sketch what the solution to that differential equation is, to what the function that has this as its derivative looks like at any point in the plane. That's the idea of what we're doing. And if we had an infinite number of little points in the plane, we could get a very, very perfect looking graph of the solution to it. We don't have an infinite number of points in our plane that we can sketch at, because that would take an infinite amount of time, which we don't have, but that's the idea. So let's look at this. If x equals 0, what does dy dx equal? And once again, we'll note that there's only x values here, so we only have to worry about plugging in numbers for x. So if x is 0, what do we get for dy dx?
1.
1 again. Okay, cool. They won't always be 1 when x is 0. That's just coincidence here. 1. So there's a bunch of lines where x is 0, the slope is 1. Good or no?
If there's like a square root, do we put plus -1 or do we just put 1?
You just put 1. This would be like that if it was meaning for it to be negative. Within an equation, a square root, or I mean, within anything in math, a square root just means the principal square root or the positive square root of it. The only reason we do, like, we have something like this, x squared equals 4, we say x equals plus or minus 2, right? That's because when we solve this equation, what the question asks when we're talking about solving a differential equation, says find all of the numeric solution, or find all of the functions that satisfy it. Well, this says find all the x values that satisfy this equation, right? So we're not really square rooting per se to get plus or minus 2. We're taking the positive square root of 4 to get 2, and we're taking the negative square root of 4 to get negative 2, right? The square root itself doesn't give us positive or negative. The square root is a positive value. Does that make sense?
Oh, okay, I get it. Thank you.
All right, so what if x was 1? What would dy dx be?
1.
1, right? Okay, good. Now, there might be some fluctuation happening between 0 and 1 that we might want to think about. We'll do that in a little bit. What about if x was 2? What would dy dx be?
1.
Say that again.
1.
If x was 2, no, I don't think so. 2 squared is 4, right? Minus 2 is 2, plus the 1 is 3. So it looks like we have square root of 3, right? Well, square root of 3 is definitely, square root of 3 is definitely more than 1, true?
Yes.
So the slope should be, steeper. It's not going to be super steep, but it's going to be steeper than a slope of 1. And it doesn't need to look perfect. It just needs to look pretty good. What if we went to x equals 3? What would dy dx be?
Root 7.
Root 7, right? And that's just going to be even steeper, right? And we would probably note that the further to the right we went, the larger x values we put in. X equals 4 is going to give us the square root of 13. Right? X equals 5 is going to give us root 21. These are just going to keep getting steeper as we go out to the right. Would you all agree with that?
Yes.
What about if x is -1? What's dy dx going to be?
Square root of 3.
Square root of 3, so we're going to be back to like these ones that are a little steeper than 1, but not crazy steep. And what if we continue to the left, like -2?
Root 7.
Yeah, and what's going to happen if we, I should make that a little steeper. What's going to happen if we keep getting larger negatives that we put in there?
It'll get steeper.
It's just going to keep getting steeper. And so it sure looks like, suppose we chose this point to sketch through. Well, it should be about 1, about 1. And maybe we were saying maybe we should look in between 0 and 1 just to see. What about if x was a half? What would we get? Just out of curiosity. We're not going to sketch these ones, but just to have an idea, we get a fourth minus a half, right? Which is negative a fourth, plus 1, which would be 3/4. So we'd have the square root of 3/4, or root 3 over 2, which is less than 1, so it'd be just a little bit less steep. So it should flatten out to a little less than 1 here, then go back up to 1, and then continue getting steeper, and get steeper down here. And we get something that looks about like that. It sort of looks like a cubic. It's not really a cubic, but it generally looks like a cubic. Good or no?
Good.
Yeah, and that's what a slope field is. That's what it does. It shows us what the solution to a differential equation through any point looks like. If we'd chosen a point up here, we just have, a steeper thing. It'd get way steeper, way quicker, and then it would take a little bit longer to get steep up the other side. We could sketch a solution through any point. So tomorrow's Friday, right? Yeah, tomorrow's Friday. Tomorrow we're going to look at what happens if we throw a second variable in there. So we're going to have somewhere it's like plus or minus. We're going to have somewhere we have a quotient or a product between the two variables, and try to sketch slope fields for those. And then we're going to see if we can find some techniques to solve some of those differential equations.